Good wishes, students of Physics 103. This is our second lecture, which I call 1B. Last time we had only an introduction. Now we will be really diving into the details of the course. First, mathematical preliminaries is vector calculus. We'll go through briefly, and this vector calculus at this level would be useful in any course which involves fields, flows, and flux. And believe me, there will be many courses in which you'll be finding this language, this mathematical toolbox useful. So let's start off. What is our motive? Motive is setting the language and grammar for rest of the course. Uh, the mathematical toolbox required to study fields, flows, and flux are, of course, you already know. This is gradient, divergence, and curl. You have used the curl and gradient to some extent in the last course, but we'll use these three to very intensively in this course. And all this we require in Cartesian, spherical, polar, and cylindrical coordinates, the three orthogonal coordinates that we'll extensively use in this course. And the calculus would be not the simple one variable calculus that you are so familiar with, but it's the extension of that is multivariable calculation with chain rule of differentiation, line integrals, surface and volume integrals involved in the day-to-day lectures of this course. The advice at this stage that it's in your dexterity in handling this mathematical preliminaries at this stage will greatly facilitate your progress in this course. And hence take this seriously and put in some amount of serious time into this right now. It requires sharpening your intuition, not just mathematics, okay? But of course it requires finger exercise. And practice it by diving into details and don't miss a step, okay, while doing this. Later, you would not need this so often, but at this stage, you require a lot of that. Now, let's start with what are fields? Is a body, let's say cricket ball moving with velocity v is a field? No. What fields require is that you'll have to have a domain of your interest in which with each point in the domain, you associate a physical variable, which could be either a scalar or a vector. Example of scalar field. Suppose in this room that I am sitting, at each point in the room, there is a temperature associated, and that's a temperature field. And it's a scalar field because temperature is scalar. There is a pressure in the room, and it could be electric potential, okay, which is a scalar. So these are examples of scalar field. There is a lot more rigorous definition of field that you will find in mathematics as you grow, but at the moment this is good enough for us. And field can have flow. For example, variations in temperature from point to point leads to heat flow, okay, or it could lead to airflow because of the pressure differences. Electric potential differences leads to free charges flowing from one region to another. So with fields, an important thing is to how flow occurs, okay. And what are the examples of a vector field? It is could be fluid. Air is a fluid itself. It is blowing. Okay, so that could be velocity at each point in space associated with the velocity of air, or in a bulk, a liquid moving, a river moving inside the bulk of the river. At each point, there is a velocity associated with the liquid. Okay, or it could be field or force that we know, or the current. Now, how do I get to understand the characteristics of a particular field? I need to understand where, especially for a vector function, how is it flowing? In which direction is it flowing? Like the air, for example, we want to know, or is the air circulating? Is it going round and round, or is it flowing like this? Okay, so these implements you must have seen in airports for the pilots to know whether the air is rotating or the air is diverging. Uh, so question that we ask is, how does the field change at any point in different directions? That's something. So if I go to any point, then around the neighborhood, how is the field changing? That tells us something. If I know that, I know a lot about that field. Okay, so let's go ahead. Let's take an example of a field. Let's say 2D field. Okay, so this is the intensity of a light. Okay, so that's an intensity of light, and this is this is 2D. These are two directions. This is the vertical, and this is the horizontal. And what is plotted in the this axis is the intensity, watts per meter square. All right. So you can see that this is zero intensity. That means dark, and then in the middle it rises. It's like a sort of a peak. All right. So this is, since it is two dimension, I can plot it as two dimensions on this side, and the third dimension is the quantity that I'm plotting. In this case, it is the beam intensity. All right. I could take a cross section and then plot contour lines of constant intensity lines. All right. For example, these are constant intensity lines, and that also tells us about the beam. This is the vertical direction, this is the horizontal direction, and these are constant contours of intensity. Okay, so these we can see that if the center portion is extremely bright, and the outside is indeed dark. Okay, so this is dark field to very high intensity plotted. There are many diagrams that will come across in your scientific career which will be plotted like that. How about a 3D scalar field? This is temperature. Okay, there is something hot inside the cup, and so there is no fourth dimension to plot the temperature. Okay, and hence it is just color coded to tell you how is the scalar field changing in this domain. Okay, examples of 2D and 3D vector functions, you are familiar to some extent. So with each point in this region, for example, there's an arrow which tells me the direction, and the magnitude of the arrow tells me the length of the arrow tells me the magnitude. All right. So with each point, and hence, and this is a 2D sketch, and then I get a feel for how the vector function is changing in this. This is important. Going to be sketching such things is going to be important to intuitively figure out the behavior of the field. This you might be familiar with already. This is a 3D vector function. This is minus r. Okay, so that is the magnitude increases. This is I could say this what is plotted is in three dimension is the minus r. Okay, so the as I go close to the origin, it's becoming smaller and smaller, and finally zero. As I go away, it is larger, and is all pointing towards the origin. You are familiar with such. Okay, so this is another sketch for a 3D vector function. Your ability to sketch vector function is an important aspect of this course. Okay, any sketch or diagrammatic representation helps at least most people, okay, appreciating the qualities of the field, or or in actually any quantity in some sense. So at this moment, you can even stop the video and try on your notebook sketching this function. Okay, so this is a two-dimensional function. Try and it's a vector function, and so try and figure plot this, okay, representatively. Not plot really, this sketch, so that you get a qualitative idea how the vector function changes. Okay. Similarly, you can try this. Please try. If we're if you get it, either from memory, or by actually looking at the quantity and then worrying about it and then plotting it. Okay, well and good. If you can't, then no problem. We will be doing such many such sketching of vector fields as we go along, and you will understand. So I really advise you to stop at the video at this moment and check that you can actually do that. I was hoping that everybody should be able to do that if you have done the Physics 101, Physics 102, which is a mechanics course. But anyway, um, let me give you a hint. Okay, so let me. There's many ways of doing it. If you recognize it, of course, it is very easy. Okay, because if you recognize that A is nothing but R vector in two dimensions, or you could write down as R hat. So there's a magnitude and that's the direction. All right. And that is, I'm sure you can do that as soon as you realize, or you could start from these X being on the x-axis, Y being 0, and they're pointing in this direction, and they are smaller to start with, and they're, as they grow, okay, they become large, and so on. Okay, so similarly, this is here, this is grows become larger, this is grows larger in this direction, and in all, at least the axis is very clear on the axis. Uh, in this small and then large, even this will be like that. This is small, this is large, and this is larger, and so on and so forth. Okay, so let me point at some. All right. So these are in these directions. Any directions can be done. It's also, you can realize that these are actually the constant. For example, here the constant is actually circle. Okay, the this will be as we go. Okay, these are normal to the circles at different. Okay, so this is the constant because the magnitude is depends on r. Okay, and similarly, what is this now? Let me. What is this? This is, if you realize, okay, this is theta in the, if in your course so far you might have called it theta, is the theta of the x-axis. Okay, and in what direction it is pointing? In theta hat direction. You may or may not realize this, but this is, in that case, okay, this is really, let us plot that out. Okay, so it is of course is again increasing. Okay, sorry, this is, I already had made a mistake. Okay, this is r. Um, this is really because the magnitude is still r, y square plus x square. Okay, so this is really, this is r increases, the length increases as we go away from, but it is pointing in theta direction. Okay, because you could write down this as minus r sine theta I plus r cos theta j. Okay, so if you take r as common, then of course r minus sine theta I plus cos theta j, which is nothing but the theta hat. So if I want to now plot this, okay, so this will be the same theta, so direction will be the same in each of these, but as they grow, as they become larger. Okay, so on this side also they grow, become larger with r, but pointing in the theta direction. Okay, and theta direction changes from place to place, right? So here it would be growing like that. And what about in this region? Of course, and forth, and this, and so on and so forth. I hope I made sense in doing that. Okay, so and in this direction is large as it becomes smaller, and then so you can see that the two, and I just thought that you are familiar with these two vector functions already from your last course. And so let's go to the first concept that we require in vector calculus, that is gradient. Okay, and that is experienced by every mountain climber. How many of you recognize this mountain? The mountain is a very famous mountain. It's the Fuji mountain in Japan. I just chose this because it has such a nice shape. Okay, and what are these red lines that you see? These are constant height contour. Okay, so this is from the mean sea level. Okay, how far, how much, what is the meters? Okay, so all the points which have the same height from the mean sea level are plotted in this contour. This contour, 2000. So how high it is? 3,500 meters. There's nothing compared to Everest, but is that flat top. Okay, so these are the contour lines in a topographic maps. Okay, so it can be done any scalar, and height is in this case is a scalar quantity. All right. Um, so how does contour, what is the relation between contour lines and steepness? That's the question that okay. So I've taken it from a geography. So you can see that if I show the mountain is like this, okay, and this is the mean sea level, and I take this height, and then you can see how it is related to the contour lines. Okay, you can see that the spot elevations are heights between the contour lines. Okay, and when close together, when the contour lines are close, okay, which means that that's a steeper slope. Okay, when the contour lines are far apart, okay, then there's a gentler slope. This is a gentler slope. So on this side you can see these are so this is the level is 10, 20, 30, 40, 50 where we have chosen. And so now the same difference of 10 comes about in a very small height, and hence the contour lines are closer. Okay, so it's important to understand wherever the contour lines, okay, if it's plotted like 10, 20, 30, 40, 50, and they're closer at the same interval, they're closer means it's steeper here and is less steep here. Okay, so gives an idea that the gradient is, or generalized slope, which we are going to do mathematically, okay, is a lot higher here, and the gradient of the slope is lot less here. And so there's a connection between gradient and the contour lines. That's what I wanted to illustrate with this. Now let's come to the scalar field and its gradient. How steep is the change at a point? So I'm a mountain climber, let's say, and I'm standing at one point. Okay. Now, if I look around, the height would be changing all around me in many directions. Okay. So how do I know what is the slope? I ask for how steep is the change in the point. Okay. So let's say I want to find out how the scalar field T could be temperature, could be height, okay, changes if I move along, okay, any direction, dl. dl is the differential length element, okay, in our notation. So, and then in Cartesian coordinates, dl is, if I will be composed of changes in the x direction, changes, differential change in y direction, and differential changes in z direction. Of course, is a vector. Okay, so if I want to find out, if I want to move in any particular direction, how much does the scalar quantity t change in that direction? That's something that as a climber or anybody, I would like to know. Okay, for example, do I want to take the steepest, or do I want to take the less steep direction to go, to move? All right. So change in, so this is the quality, the change in the scalar quantity, so dt. And I'm saying that that can be composed of, that if I know continuously how does this scalar field change if I go in x direction, how does it change in in y direction? How does it change in z direction? If I know these three, okay, then I can sum it up saying that I know that this scalar function changes in x direction by this amount. And then if I go by dx, I would have covered that much. And hence, if I go in the dl direction, I would have changed by dt. Okay. So, and this I can write down, okay, this is a scalar quantity, okay, dt. So that is the total change. But I can write down as a dot product of two vectors or vector-like quantities in which one is composed of actually the rate of change in the three orthogonal directions dotted with the direction that I wanted to move. Okay, so that's, and and hence I can, and I define this quantity which will be required. If I know this everywhere, then I can do it for any direction. And hence I define that quantity as the gradient of t at that particular, okay, and this I could find out for any particular point. Once t is given, I can find out t x y z is given, then I can find out is the gradient. And then if I want to move in the direction of dl, the change that I will suffer in dt is grad t dot dl directly from here. Now I have done this in Cartesian coordinate, but this is coordinate independent form. This is a vector formulation. All right. So where grad t now looks like, okay, delta t is a vector quantity now. So t was a scalar field from where I have got a vector quantity grad of t, uh, which is del t, okay, by del x, okay, del t by del y, and del t by del zk. All right. Um, so it's a vector consisting of partial derivatives along the length of unit directions, okay, in the different directions. Now, uh, so I could write down, okay, also since I know that is the angle, really, if suppose, what I'm saying is, suppose grad t at that particular point, okay, is figured out in that direction, and I want to move, let's say, in this direction, which is dl, in some direction, and the angle between the two is theta, then it is the dt amount that I'm going to go is simply the projection, okay, of uh, grad, is a projection of this onto the dl, okay, dl cos theta. So, and hence I can, so, and when is it maximum, the change? The maximum change in the scalar quantity at that point would be this grad t dl, because cos theta will be maximum at 1. All right. And hence I can say that grad t is always in the direction of the maximum change at that point. It's extremely important to realize this. Okay. So that sets the direction of this vector quantity grad of t scalar. And what is the magnitude? Magnitude is the slope in that particular direction. The slope can be different in different directions, but the magnitude of grad is the slope in the direction in which maximum change occurs. Okay, so from here I could from here I could write down, okay, that dt by dl, that's the slope, right? The slope is grad t cos theta, magnitude of grad t cos theta. All right. And when cos theta, the slope is maximum, okay, when the my dl itself is in the direction of the grad t, the cos is 0. All right. So these are the two qualities of the grad that are extremely important. So it's a vector whose direction is in the direction of the maximum change, and the magnitude is the slope in that direction. All right. Let's go ahead. So this is a vector quantity, okay, and at all points is in the vector field. Now, what are the properties of the gradient field? I've already said that a little bit. So first thing is in Cartesian coordinate, it does look like this, as I've just said, okay. If I move along constant t surfaces, okay, that is a constant t meaning a surface or a contour, okay. If constant t is the same, if I move along in that, then dt is 0. Okay, so then what is, since the dot product is 0, okay, what does it mean? It means that delta t is perpendicular to dl. So if it is a constant contour, for example, in the contour example, if I say that it was, let's say, a constant height, and then grad t at any point would be, because this dt is 0, so grad t would be normal to where, whatever is one of the important properties. If it is a surface of constant uh, quantity, okay, in 3 dimension, or a line, then the grad t would be perpendicular to dl. Okay. Uh, so dt max is of course grad t dl. I've just said that. So I'll, from the two properties that we have learned from the last slide, okay, perpendicular to constant value surfaces or contours, or equipotential surfaces or lines. Okay. So for example, we know, okay, these are the contour lines, and the in which direction it will maximum change. So I go at that point perpendicular to continue. Suppose I want to change in what is the maximum change, then at this point it will be contour to that. At this point it will be grad t would be that. At this point grad t would be this, and so on and so on. Okay, that's an important property that we have to mind. So gradient is more where constant surfaces or contours are closer, which I had said even earlier. Okay, so let's take an example. There's a gradient in Cartesian coordinates. Okay, so the simplest example that I could pick up, let's say, is an f of r, which is 1 by r root over x square plus y square plus z square. All right. So then, what will be my grad of f? Is simple. Okay. So grad of f would be del f by del x. So let me calculate one component. Del f by del x is x square plus y square. So minus x by r to the power 3 by 2. And by symmetry, all these will also be the similar. And hence I can write down that grad of 1 by r, the scalar, okay, is, so this quantity is common, as minus picks up from everybody, xi, yy, so is minus r by r cube, okay, or 1 by r square in the direction of r hat. All right. So, um, so this is, okay, this is an important relationship we'll use in this course, of course, okay, a lot. The gradient of 1 by r, r is the distance from the origin, okay, then it is minus r by r square. You can, this is also true for, in this course, we'll use this fact that suppose I have an xyz coordinate. This is x, y, and z. This is my origin, O. Then I could be at any point, let's say r prime. And then I could be measuring distances from there. Okay. So this is from the origin, it is at r prime. So I'm calling the prime coordinate. But suppose I'm interested in point P, which is here. Then this vector is the vector which we're using constantly in Griffiths uses in its book. He has made this popular. Uh, the this is from these, this is called the field coordinate, the P, and this is from the source coordinate. But this source coordinate itself is different from the origin. So this would be small r, because point P is small r from here, and this is at, but this quantity is r. So it's just shifting the origin as if from here to here, but this is my origin. So in that case, this is the symbol that we'll use. This is like r. I'm writing down the way I write it down. So you can minus r and minus r prime. So this would signify it is from the origin. Coordinates are from origin. This would signify it is a distance from this prime. Okay, so this is a symbol that we're going to use, and this is, you can check that indeed this is also true for if I take this distance from my r prime coordinate, this also is true that this would be r hat by r square. Okay. In fact, this is the one we'll use most of the time. Okay. All right. So the we have now, in discussing gradient, we have found some, that object which is called as del, and we call that as an operator. Okay. So this quantity, which is just this del by del xi, uh, del by del xi, del y j, and del by del zk. So this is an object. I'm calling it an object because there's no nothing physical about it. It's just a mathematical object. Okay, and so it is not a vector, but it's vector-like since it operates on components. Okay, it derives its meaning only from its action in different avatars. It's always hungry to operate on something. Okay, for example, in this case it was 1 by r. It could be any scalar which is grad t. Okay, then in this case it will become grad t and grad t. So it is hungry to act on something given to it on its right. That's a scalar. All right. So in gradient, this that we have already seen, okay, it acts on a scalar to produce a vector field of maximum directed slopes. And soon we will see that the same del as an operator, we can use it in divergence, which we are coming to next. It acts on a vector field to produce a scalar field which locates where the sources or sinks for that vector function. That's divergence. Okay, and it acts in curl, okay, on a vector field to find out where are the vortices, where is it rotating. Okay, so this operator, and that's why this operator, this is this operator itself, okay, is, if I just this operator, del is an operator, it acts on something, okay, is important. It tells us about the gradient if it acts on a scalar. It can act as in a divergence. We'll see that in a dotted with, then with the vector function, it will give its divergence, which locates where are the sources of that vector function. And in curl, it tells us about where are the vortices of that vector function. All right. Uh, okay. Okay, why is it not changing? Okay, now we'll look at divergence. We have done gradient. Now we'll look at divergence. This is trying to find out divergence of a vector field. Okay, is uh, is like searching for, okay, the sources or sinks of a vector field. Okay, what we're trying to figure out is where do they start and where do they end. If there's a sink, then they're going down. For example, water. If there's a tap, then there's a source. If there's a drain, it's a sink. All right. So flowing water can have sources or sinks, and divergence, you're trying to find that out. Uh, so let's say there is some vector function, 2D vector function given. I want to a small differential volume. I'm drawing it large, but it's let's say small differential volume in that. Okay. Then I try and find out how much is coming in, how much is coming out of that vector function within that small differential volume. Okay. So if the net field lines entering and leaving the volume is 0, there are no sources or sinks inside that volume. That is, the divergence is 0. Okay, there is no new tap, okay, in here. Okay, so there is no extra source. Whatever is coming in, let's say whatever is going out, then the divergence is 0. Okay, so I could have some more complicated vector function. Okay, and that could be this. And there also I want to find out. And then if the net flux crossing, now I look at what is the flux which is crossing this surface. Okay, if the net that is coming in, coming out, okay, if I sum it all up, if that is positive, then we say there is some source inside, because there was, let's say, more vector function fields were coming in, but there were less going, there are more going out, okay, from what is going in, which means there is a source, which is, so which means within this region there is a positive divergence. Okay, if there were more coming and less going, then that means somewhere it is losing. Okay, there must be a drain. So this is the physical meaning of real divergence. If it is positive, then I know within that region there is a source, and if it is negative, then there is a sink, okay, or a drain. All right. So let's make it mathematical. That's the physical idea. Okay. But let's make it mathematical. How do I? It is indeed uh, the del operator that comes to our rescue in measuring at each point in the. So it's a point function. That is, if I do this dot product of the del operator that you have figured out, okay, with each point, with any point, okay, I can say that is the divergence of B. Okay, so divergence is simply sum of the vector functions. How does the vector functions x change with delta x? How does the delta? So if I sum it up, okay, then it is changing in some direction, which means and it could be changing only if there is either a source or a sink, and hence it is divergence. It is that simple. All right. So this I can always write down as my operator. This is an operator willing to act on something on its right. In this case, it's the dot product with the vector function at that particular point, vxi, vxz. Then you can see that you obtain this. And that is how we can write down that divergence is nothing but the del operator dotted with the vector function at that point. Okay. So suppose, let's take an example. So let's say V is equal to R, which is X, I hat, Y, Z, and Z, K. Okay. And so this, we have just plotted it. Okay. A few slides back. And then this is a cartoon picture. This is a three-dimensional picture. This is only two-dimensional. So this really in reality might not look like this, but it's in two-dimensional representation. Okay. So in that case, now what would be its divergence? That's the question. Okay. So divergence we can calculate, just operate. So delta Vx. So each quantity will give us delta x by x, delta y by y, plus delta z by z. And hence divergence is the scalar quantity 3, okay, at this point. What am I talking about this? Divergence at the point, I'm worried about this, at this point. So the divergence of at that point, okay, is 3. Okay, because in each dimension, it increases equally well, equal. All right, let's take another example. Suppose the vector function is only pointing in the z direction, okay, in the k direction. Then the sketch would look like that. Okay, so the ones which are this is k in space, and that's why they're displaced. Okay, and then if I take what is the gradient? There's no gradient. Okay, it's in the so there is the same. It is unit, magnitude is unit, and the only thing that survives is the vz, but delta uh, constant by delta z is 0. So divergence of k at this point is 0. In fact, if it is all k, then divergence is 0 everywhere in this field. All right, here the divergence was 3 only at this point. Okay, but here it is 0 everywhere. Okay, so let's take, suppose I had z. Okay, now I have had said it's so what would be the divergence? 1, because that's the only direction delta z by z in it which is changing. So I'm just trying to give you a flavor that is not the geometry. Divergence doesn't mean that it should look like this. Okay, this divergence is 0 here, divergence is 1 here. Okay, the only thing that is, if I take a point here, then it is increasing in the z direction linearly, at least in one direction, and it's a scalar quantity, okay, which comes out of this. So I hope you have got the both the physical. So now we have both the physical feel for what is it trying to measure at any point, and mathematically how to obtain it. Okay, this is a dot product between the del operator and the vector function at that point. Okay, so divergence is a scalar and measures the strength of the source or sink at that point. Okay, that's the okay. So now let's look at the third differential that we need. There's the curve, and that, as you can already see, is the integral. Is there now a cross? Okay, del cross v. This is a vector function. So now what does it measure? We ask the question at which points the vector function is rotational. Okay, is rotating. So let's take a surface. Okay, let's a vector function on which I want to find out whether on this surface, okay, in the is there a rotation around I direction. Okay, so is there rotation as an axis. So let me ask there's some arbitrary vector function on this surface, and I want to see if this vector function is has some component which rotates around I with I hat as the axis. That's the question. All right, so let me look at this my point of interest. All right, and this is delta y, and this is delta y, and so I can write down that at minus uh, this is yz plane, all right, because in I. So if this is my point of interest, my point of interest is this point, okay, and so this is dz. So just below dz, okay, this is fy. Suppose this is fy is minus dfy by dz by 2, and this would be uh, fy plus dz by 2. All right. So now, if so, you can think of these two arrows as the two forces, okay, acting on this as an arm. Then this is larger, this is smaller by that amount, by dz by 2, and hence this will be trying to rotate it in this direction, okay, which I is the perpendicular to axis. So these two imbalance forces, okay, will be trying to rotate in this direction. How about the in the y direction? That would be dy here, and that would be minus. How does the fz, this is the fz, okay, in the z direction, but changing in y direction by 2. So this will be this, and this will be forward in y direction here. So that would be fz plus delta fz. So now this would be trying to rotate in this direction, okay, and so turning would be now composed of two of these components. One, the Fy component, trying to turn it in counterclockwise direction, in clockwise direction, and the Fz component trying to turn it in the counterclockwise direction, and we take that to be positive. And so the turning of rotation around the x-axis is I delta Fz del y minus del y by del z. So similarly, I can work out for J and K component, and then I can see that I obtain this by the cross product. Let's say F, del cross F, del by del X. So the I component would have been given by del Fz by del Y, and uh, so Ijk del X. Okay, so that's as simple as that. So then, but this rotation can be in all three directions, and I can obtain like that. All right. So let's take examples of rotational vector functions, which so we are given by, suppose, vector function v. I just said vx, vy, vz. It's always easy to calculate in Cartesian coordinates if Cartesian coordinates are given. So let's say this is a two-dimensional. In fact, this is the same vector function that I'd given you to plot earlier in the, all right, and we have plotted this. So is it rotational? This is how we're trying to plot x, y. Okay, and so this is changing in the xy plane, and this is around the axis. So clearly this has, you can see that this is rotating. In fact, these are the lines, theta lines. Okay, so this is rotating. So let's apply the formula and write down. So this is, we write down Vx is minus y and Vy is in, this is equal to 0. And how much would this be? How much would this be? Okay, in which direction is it moving? The only thing that survives is in k direction. Okay, and which is del minus y by del y. This, sorry, del x, del x, so this is 1. Okay, minus 1. So this is equal to 2k. So this was from del x by del x minus del minus y del y. So this is 2k in this direction. All right. So that tells us that the magnitude of rotation is about 2 and axis is k hat for the curl at that point. Okay. Let's take another. Suppose it is just simply x of j. Okay, is it rotating? This looks very different from here. Okay, this looks all straight lines, but it is rotating because if I put a puddle, okay, that is, how do I, what is really curled? Suppose I have suppose I have a small puddle wheel, okay, in which I put a, let's say, on an axis an arrow, okay, and it is free to move. And now I put this anywhere. I put this arrow anywhere, okay. And if it starts rotating, then that's my measure of my the speed with the angular speed with which it rotates is my measure of curl, and the axis becomes the uh, direction. Okay, so what about this? Okay, this of course, so the only thing that is survives is this x, and you can calculate this is only a single k. All right. So at least in uh, finding out the in Cartesian coordinates, it's always easy. Okay. So we have learned so far three different differentials. One is for a scalar product getting a gradient, and then for a vector function getting its sources through divergence, and whether it is rotating or not, and its axis, okay, and which axis and how much it is rotating by curl. If I know divergence and if I know curl, I know a real lot about that vector function. So I can say with confidence that if I know its divergence and curl everywhere, then what are its sources and how it is behaving, okay, throughout the domain. And hence there is an important to carry out these two information. Now let me go to coordinate systems. So far I have demonstrated to you gradient, divergence and curl in Cartesian coordinate system. But that will not do for many of our problems, because the problems that we, or vector functions that we deal with, have certain symmetry. And so the choice of coordinate system should be should match, for to make our life easier, the symmetry of the, we should take full make full use of the symmetry of a problem. Okay, in physics, actually, that's one of the most important parts which makes our life simple. That is, there is some symmetry, and for each symmetry, we have certain mathematical convenience, in fact, physical conveniences also. Okay, so yeah, the thing that you are already familiar with is so much rectangular Cartesian coordinates system. By the way, why is it called Cartesian system? Do you know? Where does this term Cartesian come? Okay, it comes from uh, Rene, the philosopher, mathematician, okay, Rene Descartes, which famously said, "I think, therefore I am." Okay, so we say that the world is Cartesian because it can be divided into three independent axes. In that sense, all right, that's just an aside. Um, so we are familiar with this. But what is it that we know that in Cartesian coordinate system, a differential element is given by this. Okay. Good thing about Cartesian coordinate system and why you have used it so much in your school days is that the unit vectors, okay, are are constant everywhere, are pointing in the same direction everywhere. Okay, is fixed. Okay, in direction at each point in the domain, they are pointing in the same direction. That's very. Let's take a small unit volume in Cartesian coordinate. Okay, then it is we small differential volume, we call it d tau, okay, with Griffith's notation, and that will be change in dx, dy, dz, just a cube. So that's a differential volume element. All right. Suppose I want to take one of the, let's say this surface, okay. So let's say I want to say this surface. So this surface is uh, is a vector, is a flat surface, is a vector dA, is small, differential. All differential surfaces will always take it to be flat. Because the differential meaning that's so small that they can be considered to be flat. So in this case, it is dx and dz and is pointing in the perpendicular direction j. So the perpendicular to the plane direction is the dA. Okay. Similarly, you can write down for any of them. So d tau, dA, and dl. In any coordinate system, if we know these three, we are done. Okay, in most of our work, which involves either a volume integral or a surface integral. Okay, volume integral would involve dx, dy, dz if it is a Cartesian coordinate symbol, and surface integral would something like this, and the line integral, okay, would involve dl in the direction. Suppose this is dl, and that is in this direction. All right. So this you are pretty familiar with and will also going to use it. But more importantly is let's get to the next generalization, which is cylindrical coordinate system, okay, which is polar coordinates. Okay, that is in XY plane, we don't use X and Y, but use polar coordinates. And the symbol that we'll use is in with Griffiths uses in the latest edition. His different editions also use different notation. Okay, but the latest edition that you will be using, the in the XY plane, the distance of the point from the origin is S, and from the x-axis, okay, this is x-axis, this is y-axis, and is phi. Okay, so we don't use theta. Theta we reserve it for something else. So in polar coordinates in this course, we'll in the plane polar coordinates also you'll use phi. All right. So then the unit vectors are, let's say, s in this direction, phi in this direction, and k. So they are the perpendicular. So if I take this point, my p, then okay, so that's my k direction is here, my s direction is here, and my phi direction is here. Okay, so s hat, phi, phi hat, okay, and my k hat direction. All right. So how do I now define a volume element? Volume element will be, of course, if I go in the unit direction s hat, that will be ds. Okay. In the phi direction, this will be s d phi. It is okay. So this direction will be s d phi. This, and of course this is a dz, and hence the volume in cylindrical coordinates is d tau ds, okay, s d phi and dz. Okay, so how do I write differential surface elements in cylindrical coordinates? Okay, we can say what will be the surface, how do I write this particular surface? I have put an arrow there. Okay, this will be pointing in k direction. Okay, and this is ds, this is ds, and this is s d phi, small. All right, so dA, and it's pointing in k direction. Okay, the below one would be pointing in the minus k direction, just vertically below that. So this one is pointing in s cap direction, and it would be s d phi dz, right? The height is dz, and the width is s d phi. Okay, and in this one, this is pointing in minus phi direction. Okay, and it will be simply ds and dz. This is ds and this is dz, and pointing in minus phi direction. All right. So our ability to write these surface elements is going to be important. All right. So a differential volume element, of course, we know. So now let's go to the spherical polar coordinate system, which I believe you must have used in physics 102 also. You are already familiar, but just a quick review. And we'll follow this symbol. I'm also fixing the notation in the whole course. Okay. Please use only the notation in the latest edition of Griffith. Okay. So I, J, K, and suppose this is a point P. Okay. Uh, so that is denoted by three independent variables, R, then theta is the angle from the K direction. Okay. This is theta. Okay, and phi from the x-axis is the phi. And and then what is the component on the k-axis? R cos theta, obviously. Okay, what is the component on I-axis? This uh, R cos theta. This is R sin theta, and then projection of R sin theta onto I-axis is R sin theta cos phi. Okay, and so so this is r sine theta in the y-axis. Okay, and uh, okay, so the coordinate the problem with cylindrical coordinates or any polar coordinates in spherical polar is and cylindrical that in cylindrical the k direction is of course fixed always. Okay, but s hat and phi hat keep changing at each point. Here all three will keep changing at different directions. Suppose I take another point here, then it would be pointing, r would be pointing in this direction. All right, and theta would be pointing in the positive theta direction. Right, so this will be, theta would be pointing in this direction. Okay, and phi would be pointing in the perpendicular direction. So at each point, the r hat, theta hat, so uh, the unit vectors change their direction, and hence while differentiating, okay, we'll have to be careful which care you must have taken in mechanics 01, because there also this unit vectors could be changing with time. Okay, the direction. So the terminology is, of course, radial distance from the origin. Theta is the polar angle with respect to z-axis. These things are fixed. And phi is called the azimuthal angle with respect to the x-axis. These are conventions, okay, and we'll follow these conventions. So what is a dl here? Dl is, of course, change in drr. In the r direction, you can only change the r. Then in theta direction is r d theta t. This is suppose this is r d theta. Okay, then in this direction is r d theta. This is d theta. So in this direction is r d theta and is pointing in theta hat direction, the positive direction. Okay, and r sine theta d phi, okay, is in the phi direction in this. So r sine theta is here, and then change in d phi, okay, will point in this direction in the phi direction, and it will be r d theta, r sine theta d phi. Okay, so how about surfaces here? Let's see surface and volume elements. So then, okay, so I just showed r sine theta d phi, okay, and this is r d theta, and this is dr. Okay, so differential length is, of course, okay, this is important. This will be almost at your fingertips. You should not have to think, okay, the unit what are the differential length changes in the three independent directions in any Cartesian coordinate system. Okay, that's, you should be able to write down in your dream. So differential volume d tau, okay, is just that, dr r d theta in this direction, and of course r sine theta d phi in that direction. All right. So let's talk about this surface. This surface is this surface would be pointing in r direction, and it would be r sin theta d phi. Correct. Okay. So this is uh, this is r d theta. Okay, and in this direction is r, in this direction it is r sin theta d phi. Okay, and is pointing in r direction. All right, this is r d theta, and this is r sin theta d phi. Okay, it's pointing in r direction. That is, suppose the below one is pointing in theta direction. Okay, and dr and r sin theta d phi. Okay, but pointing in theta direction. And what about this surface? This practice is important. Okay, so this is in pointing in minus phi direction. Okay, and this is dr r d theta minus phi. So this ability to write down, okay, the surface length and volume elements are important. Okay, and that's why I'm giving it such time and space in this lecture. All right. Now, so far, I have done gradient in only in Cartesian coordinates. What about gradient in different coordinate systems? Okay, so this is given in an appendix, but the trick that we'll use is in Cartesian we know the length code. Okay, then in cylindrical we know the length, summarizing ds s hat plus s d phi phi plus dzk. Okay, in spherical coordinate system, of course, we just wrote down dr r hat, r d theta theta hat, and r sin theta d phi phi hat. All right. So all this I can write down as if this is okay, as if that is in general. Okay, just a minute. Okay, in general, DL is, let's say U, V, and W are the differential elements in the three coordinates. So, for example, is U is X, Y, Z, V is Y, and W is Z in Cartesian. U is S and phi and Z in cylindrical coordinate system, and this is R, theta, and phi. So I'm generalizing. So as if there is a FGH, which is the weight in the differential element. This should still have, see, this is length element. So FDU would be length element in the direction of, in that particular orthogonal direction. GDV is the length element, okay, dimensions of length, and in the V hat direction. And so FGH are the weights which make the differential element, okay, as the length dimension. All right. So in Cartesian coordinates, of course, the FGH are all one. Okay. So that's why DL is dx, dy, dzk. In spherical, the U is r and V is theta and W is phi, but the F is 1, but G is r. Okay. In spherical, r. R d theta makes it a length element. And H is r sine theta. R sine theta d phi phi. In cylindrical coordinates, F and H are 1, but G is S here, right? So the definition of F, so now you understand. In some books, they write this to be H1, H2, H3, and U1, U2, U3. Okay, it doesn't matter. But so in Griffiths is given in this notation. Okay, so the gradient then is really, okay, is grad t. So you know what is the grad t by definition itself? It is change in the around that length element. So FDU is the length element in u direction. So delta t by FDU, delta t by GDV, and delta t by HDW, H dou W. So if I knew the length elements in different directions, then I can write down the grad t. Okay, change in along that unit length in that direction. All right, and hence Just if I apply, and from there I derive this U, V, W, and F, G, H, and then this, this of course we already know, and in then what is becomes gradient in cylindrical coordinates. Okay, delta t here is s d phi, because that's the length in the phi direction, this in the polar, in the xy plane, and this is del z. So this, the s is the, okay, so this sg is this. All right, so and the gradient in spherical coordinates, delta t by del r d theta in this direction, r sine theta d phi in this direction, derived from dl from here. Okay, so now I know gradient in all three coordinate systems. Okay, so similarly, I can now, I've illustrated this. Similarly, I can work out divergence. Okay, divergence is given by this formula. You don't have to derive it, but it's good to remember this. Divergence of A is 1 by FGH. Okay, the first term is differentiate only. This is scalar, you remember. Divergence is scalar, right? So there's some, but there are weight functions here appearing. Okay, so this is AU coordinate. So let's me, so divergence of A in this is of course Cartesian. In you can see that in cylindrical, this is 1 by SDR, right? Because this is 1 by FGH, and this is GH, and GH. Uh, so F and H cancel because it's, but S remains. So 1 by S, SAS. Okay, here 1 by S d phi, A phi. And this is the cylindrical coordinates, divergence is this. Okay, and in if I do this and simplify, then this is the first term is simply 1 by r square, but there's a weight function r by r square. R sine theta d theta, there's a sine theta here, r sine theta a phi. So now I know divergence in all three coordinate systems, Cartesian, okay, cylindrical and spherical. You really don't have to remember them, they'll be given to you, but it's good to know even if you're not given while you are doing a problem, you can always obtain from here. You don't commit to memory, but you should always be able to obtain DL from there, this, and from there you can get this. Then you will not go wrong. All right, but these are normally given at the back cover, the front cover, inside cover of the book, or in the question paper you will be given this, okay, while solving the problem. So you can keep it handy, but it's good to know that there is a generalized function which will give you divergence. Similarly with curl, all right, curl in different coordinate systems. So dl, we know this. Okay, so you can write down del cross a is really, okay, 1 by fgh. That means in spherical coordinate system it will be r sin theta. Then the weight function goes with the unit fu hat, g hat, h hat, and f. This is del by del u, del by del v, del by del u. And so even the vector function, the components of the vector function are given the coordinate system. Actually, this should not be x, y, z. This should be f, a, u, a, v, and a, w. All right. Okay, so this is generalized. So in Cartesian coordinate system, of course, we already know. Okay, uh, this is simply ax, ay, az. And in cylindrical coordinate system, okay, this is, you can see that this is s here and s here. Okay, this is del by del s. Okay, so here is one s1, here one s1. Both both weights are multiplied to the components. Okay, so similarly spherical. Okay, it will become 1 by r square sine theta outside. Okay, then 1 r sine theta along the unit vectors. Similarly 1 r and r sine theta along this. So you know the curl. So you can always do that. All right. Now let me come to important is what we have done so far is first derivative, but there are second derivatives which are also very, very important. Okay, but I'll start with two null results, which also give the physical meaning of the second derivatives. Okay, that is, suppose T is any scalar field. and then I have figured out its um, let's say I figured out its gradient, then I can be sure that the curl of that gradient is zero everywhere. This is an identity. Let's prove it. Algebraically, it's very simple to do that. Let's say I could choose any coordinate system to prove it, and it will be valid for all coordinate systems. So this is grad. So I can, this is what we just learned. Okay, I can write down del cross del t, and grad t is del t by del x. Components are del t by del y and del t by del z. Okay, and the curl you can find out like this, right? So let's write it down. So let's the x component, meaning the I. Okay, so that is del y of del t by del z minus del z, do z. Okay, uh, so do z delta t by del y. So why is this zero? Because whether you differentiate first, this is partial differentiation. So whether you partially differentiate first with z and then with y, or first with z and then the order is not important, because you are doing partial differentiation, and hence these two are equal, and hence it is zero. And this I can show it for all other vectors. And hence the, if once I talk about del t by del x, del t by del y, and del t by del z, that is if I know the gradient, then its curl is always zero. All right, is an important secondary. This is secondary. Why I'm calling it second derivative? Because I have already taken the um, scalars gradient, and then I'm taking curl. All right. So that is one. The next one is, okay. So curl of gradient is always zero. Always, always. Right. Okay. So this is an important. So you already know this for conservative forces. Okay. uh, then the, if I've taken curl, you already know its curl, then its divergence is zero. If you know where things are curling, then it will not be diverging physically, right? If it is curling around. If you have taken out the curl, then divergence will be zero. Again, it is very easy to prove because it's just by doing the writing out the components. Okay, so curl is divergence is of course for each of the components del by del x, del by del y, del z, del, and these are the components of I component of the curl, j component of the curl, and k component of the curl, and that's all added up. All right, so you can see that del az by del y plus, okay, so minus um, so this is del x del y az, right? Then az del y del x is here. The del y del x, and the order of partial differentiation doesn't work. Okay, so this and this will cancel. So similarly, all of this, so del ay by del z del x, okay, and del ay del z dx. So these two will cancel. So everything really cancels off. Okay, and this is really equal to zero. Okay, so this is always true, irrespective of which vector function that you have taken. All right, so divergence of curl is always zero. Physically, also you can see, okay, it's like I give a popular example of, let's say, milk. Okay, if you have found out the gradient, which means wherever there is paneer, okay, and then you churn it to take curl. After you have taken out the paneer, can you get butter out of it? No, you churn it after taking paneer out. Okay, it will be zero. Or first you have take ghee out. Okay, churn it, take butter out, and then curdle it to get paneer. You will not get it, right? So you have to, once you take out the either the curd or the gradient. If you are taking the gradient out, then you can't churn it. If you have taken the churn out, then you can't take divergence. All right, this is very, very important. Now the next second derivative, which is important to the whole of electrodynamics, or in fact all of physics, is the Laplacian. What is the Laplacian? That is, if I take grad t, okay, and then I take divergence of a, let's say vector function. We know this, that the divergence is given like that, right? Divergence is scalar, and grad t changes from scalar to vector. Okay, I wrote that down slowly.